तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were looking into the PCI arbitration using ASM chart, and basically it is the design of arbitration and not pertaining to an application such as video compression. Although it is for an illustration, we mention about the video compression, and sharing this PCI bus here are 4 masters, namely video grabber, which will get the raw image data. It may be a PAL or NTSC sequence, or it can be SVGA format. Any color motion picture can be processed, say at 30 frames per second or 25 frames per second. And what we collect here, using the PCI bus, we communicate the raw data into the codec, whose function is to bring about the compression as. And you have actually 2 here, one is called encoder, other is called decoder, which brings about respectively the compression as well as the decompression, and as an abbreviation it is mentioned as codec. And this is the design that we will have to actually do using the Verilog, and it can be an FPGA or ASIC platform, and there will be an first in first out memory in all these masters, so that whatever is processed here will be stored primarily, and when it gets the chance in order to communicate over to another master, for example this raw data I want to communicate from here to the codec to start with in order to bring about the compression. So what we do is we make a request to a bus arbitrator, which is our present design, from independent masters. For example, this can be a request 0, and this can be request 1, then request 2, and then another which is the host. Say for example the Pentium we have can be another master, and we assign priority to this, and the top we will divide this into 2 groups. One is video grabber and codec. We assign topmost priority among the 2 groups, and the next group is fireware as well as the CPU. And among this, the topmost priority goes to the video grabber, and once again among this second group, higher priority is assigned for fireware. And fireware is a serial bus which can be connected up to 64,000 and odd serial bus here. That means to say we can compress data here and then using the PCI we can send it over to the firewire, which will in turn serialize the data and send it over the channel. And likewise from any other computer we can get another motion picture in concurrently and then process here, and the reverse process can take place here, namely the serial to parallel conversion, and then using the PCI bus once again communicate to the decoder part, which decodes, that means brings about the decompression as such, and passes over to the monitor, which is the computer monitor that we have right here, and through an interface called advanced graphic port here. And as far as firewire is concerned, its throughput is really very high, and we can very easily use MPEG streams such as MPEG 2, which is the fastest of the MPEG group, and you can also have JPEG or JPEG 2000 for still frame, then MPEG 1 or MPEG 2 or MPEG 4 and so on, and any other future can also standards can also be incorporated here. What all we need to do is only redesign the bus arbitrator as well as the core that we are developing for a particular application, and it's a maximum data that it can handle at one go is 16 kilobytes. That means to say you can communicate to and fro from the firewire up to this much size, and this is not a handicap because it will get a chance once again periodically, as we shall see right now. And this CPU has is connected to the PCI bus via what is called north bridge, and main memory is also connected to this. These are all the standard PC architecture. So is the case with AGP as well as the monitor, and this is what we are going to design. This PCI arbiter has, as I mentioned, 4 masters requesting the use of PCI bus, and they are communicated by using these signals request 0 through request 3 corresponding to the video grabber. We will abbreviate this as shown on the top, and this PCI arbiter looks into the priority that we are going to see shortly, and as per the priority it will allocate grant signals to either this video grabber or codec or and so on, and using this signal grant 0 through grant 3 is meant for this. As far as the application is concerned, you can have a high resolution color motion picture such as 1600 by 1200 pixels, and this pixel resolution is very high, and it matches, it competes with the actual photographic prints, and it is indistinguishable from prints, and so even this sort of motion picture can be processed with 64 bits and 100 megahertz PCI bus, and here this 100 megahertz PCI bus is nomenclature as PCI X bus, and if you want a much lower resolution, you can go either for PCI bus straight away, 64 bit or 32 bit, or again speed either 33 megahertz or 66 megahertz, and the frame rate it can process at the speeds that we are going to discuss is 30 here. This is normally for the NTSC format, US format, and PAL etc. you need to comply only with 25 frames per second, and assuming we have a compression of 10:1, that is to say if you have, let us say 10 gigabytes of memory, storage for a particular motion picture, so what all you need is only 1 GB after the compression is affected in the codec that we have seen here. Here the compression is brought about here, and this is a very conservative assumption, because from my experience I have seen even for iframe processing in MPEG 2 it gives 15 to 20 compression factor, and now let us see different timings here. For example, from video grabber to video codec, which is a raw data communication, would take for this particular resolution 1600 by 1200 color motion picture around 10 millisecond, and from video codec, after the compression is effected, it will send it to the firewire for onward transmission over the serial bus, and this also requires the PCI bus, and that would take only 1 millisecond, because we have said 10:1 is the compression factor. That means it takes just 1/10 of this raw data. And so next step is we send it out on the transmission channel, serial channel, and concurrently we may receive another motion picture from some other computer over the firewire, and that can be once again routed to the codec. In this case it is going to go to the decoder, and this is both are compressed data as such, and it again takes only 1 millisecond because it is a compressed fashion. And once this is processed here, it brings about decompression in the codec using decoder inside that, and then what we need to do is merely send it to the display monitor via this AGP here, and this would again be same size as the raw data, because what we have done here is reconstructed the video data, and that is how we can communicate on a network, PC network, and up to a resolution of 1600 by 1200, and this is rather a theoretical research stage. So we will have to see the real implication when we really build the system. And summing up all this, you have only 21.2 millisecond, whereas one frame time is 33.3 millisecond, taking 30 frames per second, and you have lots of room left, so another 12 millisecond or so for the host to do certain jobs such as configuration from JPEG to MPEG-1 or MPEG-2 and so on, or intermediate processing also needs to be done, which we will use host for this purpose, and naturally have lots of time available for the host in order to complete its task. And so this shows that this scheme is a viable scheme, and let us see the order of access to the PCI bus. This is the priority that we ascribe to different masters. For example, we said that video grabber and codec are in the first group, so we will give in turn topmost priorities for the video grabber, followed by codec, and then we go to the second group, whereas wherein we give only one of the masters, namely the firewire, which is higher priority than the host. And once we have given a chance to the second group, we will come back to the first group and give chance once again for both video grabber and codec, because we need to process the raw data which cannot wait, and we need to process it rapidly, and so is the case with the compression here. And once we give this, and naturally the last chance will be for the host, and as we mentioned before, host will not take much time for processing, because what all it has to do is drive the menu to start with, and then configure from one state to another once in a way. And what is very important, topmost importance is this video grabber followed by the codec, and that is the reason why we gave the priority like this, and this is what we are going to implement in the bus granting scheme, which will, and once you have given to the second group, we come back to 1 and you continue forever. So we will see how to make an ASM chart for this application such as bus grant, and let us, this is a rectangle, as you know, is a state indicator, and actual value is put here. We are going to use the decimal value because it will be easier for us to code it in Verilog, and the descriptive state is on this, and this implies we are going to wait for any of the requests to manifest. So as we mentioned before, there are 4 masters, and each of which is interrogated here whether a particular request is has been got by the arbitrator. We are questioning at this point of time, and topmost priority is for the video grabber, and therefore we question that first. Suppose the video grabber has not asserted its request, so we will go on to the next, what's called codec, and followed by firewire as well as CPU. and if none of these requests are pending, so we go back to square one, that is a wait state, and continue to wait till someone makes the request. And once a request is got, let us say the topmost priority is the video grabber, because that is the first thing that will happen in this compression system, because without grabbing the image there can be no further processing. So naturally this video grabber is the one which is going to make the first request, and it would take some time for it to process, dumping its data collected over the PCI bus onto the video coder. So that would require some time. So it will the request 0 will be asserted for quite some time, and till it is finished the usage of the PCI bus. And so long as this request 0 is asserted, grant 0 must be asserted, and that is the loop here. And next is this is also the entry point for VG state, and if this is not asserted or it has completed its request usage of the bus, so naturally the next contending master will get the attention. For example, we will see request 1 or request 2 or request 3 in that order. This is once again the same priority as we have seen before here, and the state to which it goes after the request is processed, it is asserted, it will be indicated here. So that is 2 corresponds to 2 here. So that means this is connected here, and once this is processed, we go on to process the codec grant, and once request 1 has this is request 1 I suppose. Yes, once the request 1 is asserted, we will grant the signal 1, and once again we stay here till this request, VC has processed, its codec has processed all its transactions for the current cycle. Cycle means not the clock cycle, it may be several clock cycles, and once it has finished its job, it will deassert request 1. Therefore, control will go on to the fireware and CPU, and in case they have requests pending, it will go to that respective routines. If none of these are present, it will naturally go to the video grabber, because all the 4 have been covered here. And this is for fireware grant. Once fireware has request has come, it will grant corresponding signal here GNT2 here, and once again so long as its request is asserted, it will keep revolving around this, asserting grant 2 all the time, and once it has finished its job, it will naturally go to the first group, because this is the after fireware we cannot go to the host, because only 1 is allowed in the second group. So therefore, the top next automatically it goes to video grabber, because that is the priority on which we had designed our system. And if this is not present, naturally it will go to the codec, and thereafter go to CPU in case this is also not asserted. And once again, if none of this is present, it will go to VG and do the checking of requests for all the 4 masters. And similarly for finally for this CPU, this is the host here. When host, let us say it has come from this path, it may come from any other branch also, and suppose it has come here, and grant 3 will be asserted here, and it will continue to be asserted so long as request 3 is asserted. And once it has finished its job, it will go to the video grabber, because this is the second group, second one, and naturally it has to go to the first group, and once again the video grabber being the topmost priority, control passes on to this, and it is a simple ASM chart, and for which we can see the code now. So we give a line comment here, and indicating this PCI arbiter is the design, and we give the same name here for module, and we declare the module here, and collect all these IOs here and separated by commas, and we have clock reset, so active low, and 4 requests here 0 through 3, and the corresponding grant signal which will be the output, and this is what we have listed here. these are all the inputs here, and these are all the outputs here. And in addition to this, these outputs need to be declared as register, because we will see that later on that this will be covered in always positive edge clock block as. In addition to this, we have also the state indicated here, and this arbiter state we will call, and this is what we have seen here earlier in the rectangles. We had put the state, say for example 3 here or 4 here. This is what is implied there, and we will be using, as we had used earlier, a case statement in order to process these rectangular boxes in ASM. So, to start with, this is the first always block, and it is reckoned at positive edge of the clock, and we have once again as usual a negative edge reset, and if a reset is present, this may be a system reset or a power on reset, and if it is present, so what we need to do is we will switch off all ground signals to start with. This is mind you, this is only a wait state, 0 state, and wherein we do not have to turn on any of the grounds here, and arbiter state also needs to be in the same state, wait state, namely 0 state. And we started with if, so we have an else here, and a group of statements were encountered here, so we need a begin and end here, and then we say else, and this is the case I have been referring to, and this case depends upon the arbiter state, and this will be 0, 1, 2, 3, 4 corresponding to the 5 rectangles that we have had, and this is the 0 state, and these are all plain decimal as we have seen earlier example also. And in this state it is nothing but a wait state, so what we do not have to do anything except turn off all the ground signals. And now we will examine corresponding to the very first interrogation block that we encountered in the wait state for a request, that was a diamond there on the ASM chart, and that translates here as an if statement here. If request 0 is encountered, and this is corresponding to the video grabber, and what we need to do is we have to take it to state 1. We are presently in state 0, we will take it to state 1, because in state 1 only video grabber is granted its corresponding grant 1 signal, and otherwise go to the next waiting master, that is video codec, which corresponds to state 2, and that is what we do here. Else if statement is what you are already familiar, that we use, and if request 1, that is corresponding to the video codec, is asserted, then take it to the arbiter state 2. If this is also not asserted, so we will naturally go for the next master, which is firewire, and once again we use an else if statement, and this time we use the corresponding request 2 for the firewire to be asserted, and if it is asserted, we take the arbiter state to state 3, which happens to be the state for the firewire processing, and so is the case for host processing, whose state is 4, and its corresponding request is 3 here, and that is what is here, is plain exactly the same what we have seen before. And if this is not encountered, so we have covered I think all the states, and what we need to do is go back to wait state 0 if none of this are encountered, and corresponding state is 0 here, that is what is the arbiter state is for. And there must be an end, because we started with begin, we are remind you we are processing only for case 0, and similarly we had to process for case 1 right up to case 4. So for case 1 we need to switch off all other ground signals and switch on only one signal, that is ground 0, because this happens to be the for video grabber, and this is an important thing. You should not forget to switch off all the unwanted grounds, and once again we look into the request 0, which corresponds to the video grabber state, and whether if the request is still pending, which indicates that it has not yet finished the usage of the PCI bus, and it should continue to be in state 1 In state 1 of course we will be in the same condition here, wherein grant 0 is continuing to be asserted here. And once it has finished its job, we need to check for request 1. This was request 0 corresponding to the video grabber. Corresponding to the video codec, it is request 1, and the corresponding state is 2. So, if this is asserted, go to the state 2. If this is also not asserted, so check for the fireware status, its corresponding request is 2, and take it to the respective state 3, and so is the case for the host, in which case it is state is 4, and we have seen that the same VG, VC are given the priority first, and then go over to the second group, and in that give only one priority. And we have just followed the ASM chart, and the ASM chart anyway reflects the priority that we have already assigned, and naturally the code must follow suit. If we have already covered for all other conditions here as far as video grabber state is concerned, and so we will if nothing else is remaining, we will say else and then take it to state 1. The state 1 is the same, we are in state 1, so it continues to be in that state. So, in state 2 we had to grant 1 here, and these are all exactly the same here, and you can see that it is in, if request 1 is made, video compressor request is still asserted, remain in the video codec state here in 2, and if otherwise check for fireware, which is state 3 as well as the request is 1, and otherwise you check for the CPU and request 3 and state 4 corresponding things. Once again, if none of this is present, go to the state 1. So, we always go to the video grabber state. That was the right side end of the ASM chart that we had seen, because we have examined all the conditions. So, no other condition is persisting, and therefore, we go back to the VG state. That is what we have seen before, and once again that is an end, once again that is a begin and there will be an end. This is corresponding to the fireware state. So, here also we switch off all grant signals and give grant only for grant 2, that is this corresponds to the fireware, and once again we remain in the same state so long as the fireware request is still made, asserted, and we continue to be in the third state. That is what we are here, and in this state, if this is not encountered, or if it has finished the usage of the bus, the fireware has finished the usage of the bus, then what we need to do is go back to video grabber, and that is what we are doing here, and otherwise go to the codec here. We have to examine request 1 and take to state 2 here, and otherwise to the host here, request 3 and state are corresponding to this video, this host, is it host? This is for fireware, and this is for the host here, and if request 3 is still asserted, remain in this host condition state for processing the same, and once it has finished its job, the request 3 will become 0, then this will not be valid. So, control goes to the first group top priority, it is a video grabber here, and the corresponding state is 1 there. And finally, for actually we are in fireware state examining different masters, and here this is the state corresponding to the host, and as usual once you enter this state you need to grant only 3 here which corresponds to the host and deassert all other grants. And so long as this request 3 is still asserted and you need to remain in the same state always granting 3 here, and naturally it will be in the state 4, and if it has completed this job this will go low and it will go to this condition here which is going to be the video grabber state, and corresponding state is 1 here, and this is the completion of case. We have covered all the aspects as mentioned in the ASM chart, and we also need to take care for the don't cares and tri-state that may be encountered and corresponding in the arbiter state. So, in which case you need to take it to a safe state, let us say the wait state here, or you can video grabber state also you can take it to. And we started with case, therefore there is an end case here, and it was in always block, and there was a begin at the start and their corresponding end is this, and we started with the module which is the design for the PCI arbiter, and naturally we will have to end with an end module. So, we will look into the test bench for the PCI arbiter. So, in this case let us say we want to run at 50 megahertz, therefore we say clock period by 2 is 10, and we need to include the actual PCI arbiter design, and that is what is this statement is for, and this is a test bench. So, we had to declare the test bench module name must be mentioned here, PCI arbiter underscore test. The same nomenclature we have been following all through has been adapted here too, and you have to naturally term it as a module here. And being a test bench, we have seen that inputs are all reg, and these inputs for the different requests corresponding to video grabber, video codec, firewire, and host. These are all requests 0 through request 3, and this will have to be declared as register, and which means holding the value, and so also the case for the other inputs such as clock, system clock, as well as the power on reset. And we have also seen in the test bench whatever outputs we have, naturally the grants signals are the outputs here, and they are grant 0 through grant 3, and they must be declared as wire because we may have several such modules called here and we need to interconnect them. So, this interconnection implies it is a net or wire, that is why we declare it as wire in the test bench. So, once we have done this, what we need to do is instantiate this design. This is the design here, PCI arbiter, and this is the instantiation we are doing, and this happens to be only 1, and therefore there will be just U1. If you had several such designs called, again you need to only change this to E2, U3 and so on. And once again we have seen this connecting ports by name, and so that we can relocate in any other order, and these are all the inputs that we are listing here, followed by the outputs, and inputs are also mentioned here. As we mentioned before, you need not separate out all the inputs and outputs, and it can be in any order, and that is the beauty of using ports by name nomenclature. So, the test bench is initialized at this point. Once you initialize, it means the time element is 0 here. So, we start with initial followed by begin, because there are going to be multiple statements here, and at the end there will be an end. And so, the comment says at time 0 let the request inputs be active. So, what we are doing here is, so we will make all the requests 1. So, that means to say there are 4 masters and all the 4 masters are asserted. So, let us see when we watch the back connected waveforms, we will see what will be given the grant. So, in spite of the fact that all the 4 are asserted, and we have also to initialize clock, and that is what we are doing here, and because we are interested in positive edge of the clock, so we naturally start with a 0, and this is a deasserted reset condition because it is an active low here. This n stands for negative, or you can just say L also there, implying it is active low, and it is deasserted here, and we assert reset at after 60 nanoseconds. So that means to say for 20 nanoseconds we apply the reset pulse, and that means once again this is restored to normal condition, which is not reset. So once the reset is withdrawn, so it starts processing from here onwards, and at let us say at after the elapse of 400 nanoseconds, and that is 480 to start with, because we have to add 60 plus 20 from 0 state, and at 480 nanoseconds what we do is, earlier it was request 0, so also the other requests were asserted, that is 1. Now we are deliberately making these changes here. At 480 we will make request 0 low, that means withdraw the request. In other words, it has finished using the PCI bus, and at 560 nanoseconds we withdraw request 1 and so on, request 2, and after at 800 nanoseconds we, let us say this is the top priority, that video grabber request, and we will assert it once again here, and when we view the waveform we will come back to this, so that we will see where we are. And after further time at 1000 nanoseconds we deassert request 3, and what has been happened here is we have only tested partially, it is not full fledged test as such, and maybe 7-8 conditions we have checked on this, and we will continue to run for some more time. It need not be 1200, it can be 100 or 200, it only is a cumulative here, and once you are through with the testing you can just stop here. So I made it a little longer here, just to have some cushion here, and so next one is we need to run the clock. So that is possible only if you toggle a particular signal. We call this clock, we initialize it to 0 earlier at 0 nanosecond, and this is being toggled by inverting and assigning it to the same signal, and this happens every time after the elapse of this much time. This we have set as 10 nanosecond. So at every 10 nanoseconds time a clock is made as its inverse. So if it is 0 it will become 1 every 10 nanosecond. That means to say every 20 nanosecond it will output 1 clock. So that corresponds to 50 megahertz, and that is how we get the 50 megahertz clock. And we started with module, there must be an end module for the test bench as well, and these are all the results. For example, synthesis results using simplify is reported here, and this is the PCI arbiter.v is the actual design, and its reports Verilog syntax is successful. And remember earlier what we had done is, see this is the ASM chart, we have given 0, 1 as the condition here, 1 then 2 corresponding to the grants of the 4 masters that we have, and this is the 4th master here, and this is 0, 1, 2, 3 up to 4 in decimal. And now let us see what this tool does. So this is what we had here, and these are all the usual report. What it says here is, what is important here is, it is trying to extract state machine for register arbiter state, and it says it has extracted state machine for the arbiter state. So what it means is, it inspects, so although we have given 0, 1 corresponding to, these are all the states here, and we had asked for 0, 1, 2, 3 and 4, that is what we have seen in the ASM chart. Now although we have asked for this, which requires only 3 bits here, that means 3 flip flops are required, whereas the tool has assigned a different manner. So, for example, what it has done is the original was what was requested was this, and what we designed was this state. Actually, what the tool after optimization is different now. It has taken 5 bits, although it has increased the number of flip flops. It has you would recognize this as a one hot machine. You can see there is only one entry here. In one hot machine, all the states should have just one entry there. So, 1 here, next is 2 here, this is a decimal weight if you take. So, and 4 here, then 8 here, 16 and so on. So, corresponding to all this. So, the tool has that much intelligence to map it to a more better optimization. So, from that point of view, the tool must have allocated this. And if you open the, if you see in the simplify RTL coding, you would precisely see what has been copied here. And before we go on to the details of this, what we will see is the waveforms after back annotation. So, for example, I will just explain before zooming here. We have a reset here, and that is applied at this point of time. So, you remember that at 60 nanosecond or so we had, and here it is marked 50 nanosecond, and each one will be division is 5 nanosecond. So, there are 10 here, and 50 by 10 is a 5 nanosecond here, and this corresponds to around here. So, that is 60 nanosecond, that is what we have here, exactly 60 nanosecond, and it remains for 20 nanosecond, and thereafter it goes high. So, this system starts working only at the following edge of the positive edge of the clock, that is at this edge. And so, here we had will zoom this. You remember that we had all the 4 requests made. So, you can see this waveform is just on the top of the number, implying that they are all 1, although it is showing 0, it was clicked at some other point, that is why it is showing 0, but actually what you should see is this is always on the top of the number. So, which means all of them are like that. So, all are 1, we started with a 1, and let us see where the first grant is, who will be given the first grant. Say for example, here these are all the grant 4 grants here, and this is the initialization state, and wherein it is made 0 here, and very first grant video grabber grant is awarded here, and that is because this will be this request 0 will be sensed only at the positive edge of this clock, that is at this point after the reset is removed, and the grant will will be issued only at the following edge of the clock, because it cannot change instantaneously. This we have seen before in monoshot also, same thing. So, it should happen here, because it is back annotated file, you should get the grant even delayed from with respect to this edge. For example, you can see here. So, this is corresponding to this point somewhere here, whereas it is here. So, this will be around some 5 nanoseconds or so, we will see in the next waveform. So, grant 0 is asserted here, and this is what your design PCI arbiter has done, and although all the 4 requests were made here, and naturally it changes state here from 0 to 1, because 1 corresponds to the video grabber state, in which case grant 0 is given here. So, in the next waveform what we have is, so grant 0 which is high here, and request 0 has gone low here, and which will be sensed only at the positive edge of the clock, and it will take effect, grant will be removed, grant 0 will be removed only at the following positive edge of the clock, and once again because it is a back annotated thing, you see a time delay here, and you can see this grant 0 is removed at this point of time, that is the delay is also mentioned here, that is 5.4 nanoseconds here, and grant is always late, whereas the state itself, now you see that because of simplify overriding our states, after state 1, 2 it has gone to state 4, So, that is what we have pointed before, and here the actual state changes much faster. This is only 1.768 nanosecond, and with reference to the positive edge of the clock, and this grant 0 is withdrawn here and grant 1 is awarded here, and which and request 1 goes low here. Therefore, after the second clock from there, and once again after a delay of 5.4 nanosecond, and grant 1 must go low. This is corresponding to the request 1 going low here, and simultaneously without any time lag, you see even at this point you can see that grant 0 is withdrawn, grant 1 is immediately given. So is the case for grant 1 and grant 2, and going to this third waveform, you see here after 4 we have got a 8 here. In this case grant 2 is deasserted and grant 3 is issued here, because grant 3 was already waiting for quite a long time, and request 2 is also gone here, and in the last waveform you can see request 3 going low here, and in between in the earlier waveforms request 0 has been asserted again, therefore it is high here, and although top priority has come here, unless the lowest priority has processed completely its usage of the bus, it will not release the bus. So only after the release of the bus this top priority can get, and that is what is happening here. It is released here, second clock edge, and once again 5.4 nanosecond delay, grant 0 is awarded here, and simultaneously grant 3 is withdrawn here, and this completes this checks the functionality right after the back annotation, and we have been looking into this 1, 2, 4, 8, 16 as the states assigned by the synthesis tool, and you will be surprised to see it is reporting very high frequency of 242 megahertz, although we have requested for 50 megahertz, and this is because we have selected the fastest available device in Vertex E series in Xilinx, and lowest capacity, which is 50,000, and the lowest package and highest speed here, and that is the reason why you get some 242 megahertz there, and it has taken a paltry 10 number of LUTs here. So the design is so compact, and probably optimization has done a good work there, and Xilinx place and route results for same or number of slices etc. it reports, and you can see the gate count here, it is just 132 gates, and if you want JTAG compatibility of IO pins, then you need to sacrifice more gates here, and here you will be surprised to find 242 megahertz reported by synthesis tool is enhanced to 294 megahertz here, but actually this will be misleading, because this is only a small portion of the total design. The total design is when you make the entire codec and put everything in the same chip or multiple chips. So that will be the true picture, in which case this may come down crashing to anywhere from 50 megahertz to 100 megahertz. And finally it will generate this bit stream, and this is what you will be using for downloading into the hardware, or if you are an open core IP core supplier, you will be supplying only this along with the documentation. And so finally we have some assignment for you. What we have done is, I will just read out the assignment. Add a 4-bit counter to monitor the bus activity after master is granted the bus. So if the master fails to avail the bus within 16 clock cycles, withdraw its grant and allocate the grant to the waiting next priority master. This means you have granted to a particular master which has requested, and even after 16 clock cycles it has not made use of the PCI bus. So what should you do? You should remove the grant for this, and without even warning, because this is the penultimate thing agreed protocol for all the masters. So you include a 4-bit counter in your design, so that you count 16 clock pulses after it is granted, and if no activity is found on the bus, which will be reported by another signal which we presume it is available to you, and then process this. So also add a 16-bit counter that keeps track of the maximum allocated time elapsed, which is different for different masters, since the time a master is granted the use of a bus. So once a master has taken the bus and started using, there is no guarantee that it will surrender the bus after elapse of its time. So you need to keep track of that also, for which you need one more counter and design this as well. After the elapse of time programmed for the master using the bus currently, withdraw the grant and allocate the bus to the waiting next priority master. And herein the design we consider only the encoder portion for as far as bus grant is concerned. I have not taken into account the decoder aspect, and video codec actually the decoder to the AGP. This is for display monitor, and a motion picture is displayed on the monitor using this AGP. Communication is not incorporated in the above design, that is what I said. So you have to include this into your design. That means you may have to add one more bus grant, bus request signal, and in order to do this. And naturally this calls for the amendment of the ASM chart, the design as well as the test bench to incorporate all the above changes. The test bench described earlier is by no means exhaustive, because we have 4 requests, so the total combination will be 16, whereas we have seen the test bench we have hardly used some 6 or 7 types of tests. So you look into that aspect, and whatever is not covered in the test you make it full fledged. Therefore include all possible permutation and combination of inputs to test the design completely, and I hope you will make a sincere attempt to solve these problems. If you have any question you can ask. Okay, thank you very much.